It's really very interesting. Okay, let's continue. 3 guys here. Perfect. Okay, let's try to start this chapter. We have some technical problems. What I want to say. So we are refreshing information. We are refreshing knowledge from the thermodynamic courses. First, before we will start discuss the working process of the turbomachinery from the position of the thermodynamic system, let's remember some properties of the thermodynamic diagrams. In PV diagram, the area which are located at the left from the process line are equal to the specific work which we are spent for the compression and which we are spent for expansion. It's depend of process, of course. If we will speak about TS diagram, temperature and entropy diagram, in common case, line of the process will be like drawn at this picture. It's line in C. The area of under the curve equal to the specific heat which we are supplying or extracting during the process. So it's 2 important moments which we need to extract from our memory before we will discuss the thermodynamic processes in the turbomachinery. So it's clear, yes? Perfect. Let's come further. Let's investigate the working process in the compressor. In ideal case, in the compressor, we are realizing the adiabatic process, and this process could be drawn in PV diagram like line in CS. So we are starting in the point in, and we know the pressure P1. Which equal to initial pressure, and we know pressure P2, which equal to final pressure of the compression process. And index S shows what we are speaking about, the ideal process without losses. What the specific work of ideal process? Could we determine the ideal work of specific process using this diagram? Yes, of course. It's equal to the area in CS to 1. Perfect. And how the real process line will be located in PV diagram? So here, a line for ideal process without supplying any heat and without losses. How the real process will be, real process line will be looks? How do you think? So. It's very simple in reality. So let's imagine what the main difference between the real process and ideal process. What's the main difference? We have losses in real process. And what mean losses? Losses usually, the simplest losses is the friction. Friction between the layers of the fluid or gases. And what do you know about friction? If you have friction, you feel the heat. Finally, energy which you are spent for the friction convert to the heat. And that's why in real process, in reality, you are supply heat. And source of this heat are friction. losses, by other words. So, and what's mean what we are supplying heat? It's mean what the temperature at the end of the process will be more than in ideal process. And we could to say this line I mean, correspond to how to say, it's a line for constant temperature. And this line corresponds to the temperature at the end of the ideal compression. In real compression, we have much more temperature. That's why final point for the same pressure will be moved to the direction with the higher temperature. It's mean here. Because if you increase temperature, isothermic line will be moved up and right. So that's why finally we will receive this line, and final point of the compression process will be located in the cross section of isothermic line, which are corresponding to the higher temperature at the end of the real compression, and line which correspond to the pressure at the outlet of the compression process. So, and in reality, in PV will be looks like in C. And you see what the angle will be much more than in ideal case. So the area 1, 2 CS in, it's the area which we are spent for realizing ideal compression. And let's try to understand what's mean area of the triangle in CSC, what it's mean. To understand it, let's imagine the compression process. So you are compressed the air. Of course, during the process, you are have some losses. And finally, you are supply the energy which you are spent to overcome loss, like internal heat, But if you remember the equation for ideal compression, let's try to draw it. This is specific work of ideal compression. This one. It could be easy calculated. This is inlet temperature, pressure ratio in degree K minus 1 divided by K minus 1. K, it's adiabatic index. So, it's very famous equation and it's very useful in gas turbine engine and the turbomachinery too. That's why I will draw this equation a lot of time. But what's the main information for us at this moment? What the work of the compression depend from the temperature. And in real process, because your temperature higher than ideal case, it means what you need to supply some additional energy to provide compression for reaching the pressure ratio which you need. So, and it's very interesting conclusion. It's mean what we are paying twice for the losses in the compressor, and it's really very interesting conclusion. From one hand, we are spend some energy to overcome losses from one hand. It's first paying. It leads what the temperature of flow will be increased, and finally, for compressing more heated gas, we need to supply additional specific work. It's second pay. And the area of the triangle, it will be additional work for the compressing more heated gas. It's really It's really impressive because we have one problem, losses, and we are paying twice for these losses. So, but of course, finally, we are interested by efficiency. And for calculating of efficiency, we need to find useful work of the useful work of the compression will be this one. We need to find this specific work which we are supplying in our process. And if we are looking to the PV diagram, we know LCS, it's the area in 1, 2 CS. We know delta LV, it's the area of the triangle, but we have no information about this value in PV diagram. That's why we need to use TS diagram to try to find the efficiency. So in TS diagram, isobaric line looks like at this picture, approximately. Of course, it's not, how to say, not very accurate picture. It's only for understanding of the principle. So in ideal case, if we have no losses, if we have no additional supply of some energy, mechanical work, what else, heat, we receive what in an ideal case compression process in the compressor it's the isentropic process, and it's mean what in ideal case it's drawn by vertical line in TS diagram. So we are starting from the low pressure and we are comes into the high pressure. So it's the first idea. Then next idea, next question, I think. How the real process line will be drawn? So we are using the same approach like in previous case. We have losses, and finally losses hit the gases. It means what at the outlet of the process, at the outlet section, temperature will be higher than in real process. And finally, what it means for us? It means what this point with the same pressure will be moved to the direction of increasing temperature in real process, because temperature at the outlet of the real process will be higher. And that's why real process line in C will be looks like at this graph. So, and let's try to find all elements of this equation which are explain a process of energy exchange in the compression during compression process in TS diagram. So about LR, this is resistance losses. This is specific work which you are spent to overcome losses. We assess what the finally this energy are converted to the supplying heat. And we know what in TS diagram, supplying heat, it's the area under the line. That's why this green area, it's the supplying heat, and source of supplying heat, it's the losses. That's why we are find the losses here. The delta LV, the additional work to compress more heated gases, like in the case of PV diagram, equal to the area of the triangle in CSC, the blue one. It's the additional work for compressed more heated gas in the compressor. And how to find isentropic work of the compression process. I couldn't explain why. I don't know the thermodynamics such good to explain it simple. But we are taking first position, point number in, and make the horizontal line to the cross section of the final pressure. And we are receiving a point M. And area NMCSC, we have two letters C at this graph, will be correspond to ideal work of the compression. LCS, it's marked here. So, and if we look carefully to the TS diagram, we could to find all elements of the specific work of last equation here. So, LCS we have it, LR we have it, delta LV we have it, and that's why we could to say what all area which have some color at this picture, NMCD, it's the real specific work which we are supplying for the compression process. And by the way, we will discuss it in future slides, but we could imagine how to calculate efficiency. We know what useful work LCS, and we are divided to all square of this figure. And I think you are clearly seeing what ideal work less than real work. It's normal and it could be explained. So perfect. It's all about the compressor. So let's do the same analysis for the turbine, for the expansion process. In the turbine, we have high pressure in the inlet of the turbine, and we have starting point G. In ideal process, we have adiabatic expansion, and it's complete at point TS, which correspond to the final pressure P4. And ideal temperature TTS. And here we draw is a thermic line which correspond to the temperature in the end of expansion process in ideal case. So let's try to understand how the real line will be drawn here. So the same analysis. In reality, we have losses. We are supplying internal heat to our flow, and finally we are receive more heated gas. It means what the temperature at the outlet of the turbine will be increased. That's why point TS in real case must be moved to the isothermic line, which correspond to more temperature. It means what it will be moved here. And finally, we are find this line, which correspond to real temperature at the end of expansion process. And because this temperature higher than TTS, line GT will be looks like at this graph. And you see what the angle of the line will be reduced. So, and let's carefully look to this picture. It's really very interesting picture. Maybe it's not seems, but I will show what I mean. What the specific work? What the specific work of ideal expansion here? Blue one, not this area. So the specific work, it's the area to the left of the line. It means this is ideal line, and the area to the left, TS for 3G. So this area, this is specific work of ideal expansion. And how do you think, what the ideal work, what the specific work of real expansion? It's very typical answer for the students. I will show to you some very interesting moment, deal with it. It's really very typical answer for the students. Okay, let's change the color. So, it's very logical suggestion what the specific work of the real process equal to this area. Do you see something strange at this answer? This is ideal work. This is real work. Like the it's mean we are so we are receive what the work which we extract from the turbine more than ideal case. It's mean what the efficiency more than 100%. And it really looks like in the turbine we could receive efficiency more than 100% at this picture. But of course, in reality, it's not true. So the area T for 3G, it's the specific work of polytropic expansion. It is not the work which we extract from turbine. It's from polytropic expansion. So let's try to understand what it's mean. How to explain? Let's try. So in that expansion process and UN expansion process, in the and as you know, so and we are some, but as you know, the losses finally looks like for the conversion. But for us, it's important what isentropic work of expansion process depend from the temperature. And if you are increasing temperature, you more specific work in the turbine. And let's imagine the process. We have expansion process, spend the energy to overcome losses. It leads to this equation. It's mean what we could receive additional work in the. So delta LV here, it's the additional specific work which we extract from the process because we are receiving more heated gas in our process. And it's a really very interesting moment. I know one comparison how to explain it. It's like bank cashback. Bank cashback. So you are paying some money for overcome losses, but you are receive some cashback back. It's really the same process. You are spend some energy to overcome losses, but some quantity of this energy return back to your process, and it's help to us to increase the final work of the turbine. It's the first interesting moment. The second moment, if we are compare working process and the compressor working process, we have really the same physical element. We have losses which finally increase temperature, but the same physical process leads to the very different conclusions, different physical I don't know how to say physical processes. So in the compressor, the increase in temperature have negative effect because we are must to pay twice for the losses. In the turbine, of course, we are paying for the losses, but finally we could to return some energy back. And that's why if you will look to the picture, to the numbers of efficiencies of compressor and the turbine, usually efficiency of the turbine much higher. Of course, in some case, it could be opposite, but it's not very typical. Typically, efficiency of the turbine are higher than efficiency of the compressor. And one of the main reasons, the heating of the working fluid by due to we have losses, had a different influence to the working process in the compressor and to the turbine. For the compressor, it's the negative influence. For the turbine, it's not so negative. Of course, as you will see, the efficiency not equal to not more than 100%. Yeah. And that's why we are not returning back all energy which we are spent to overcome losses. And if we will speak about the comparison of efficiency of the compressor and the turbine, first reason, this one. And the second reason, what in the compressor, we have diffuser process. In the turbine, confuser process. So in the compressor, the flows comes through diffuser channels. In the turbine, the flows comes through the confuser channels. In the diffuser, because we have much, how to say, the thickness of the boundary layer channel and probability of the separation much higher. Also is in diffuser channel higher than in confuser channel. It's the second reason of reducing and the relationship between ideal expansion turbine and specific work which we are finally received in the turbine. Understand it to use TS diagram because we need to know value of losses here and we have know it in PVD. So in ideal case, in TS diagram, ideal process like vertical line because it's isentropic process. We are starting and comes down to the point TS. But in reality, we have much higher temperature. Will be what the specific work we are spent to overcome loss. The same work which we are supply like external heat, and you know what the area under the line of the process, it will be supplying heat. Oh, sorry. So area E T F EGTF trapezoid area. It's the area. It's the how to say. It's the losses. This one. It's E, G, T, F. The area of the triangle TSGT, like in previous case, it's the specific work which we are returning back to our process. So that's why in reality we are lost only green area. So first we are spent energy EGTF to overcome losses, but upper triangle will be returned back to our process. That's why in reality we are lost only green area ETSTF. About ideal specific work like in previous case, we make horizontal line to the left direction. We are find point M and area CMGE. It will be ideal specific work of ideal process. Where is my mouse? Hey, sorry. CMGE. It will be ideal specific work. Do you need the rest?
I can go to the one with your thing.
Okay, perfect. Okay. Okay, let's complete it. So, okay, let's try to find all elements here. So there's CMGE, it's ideal work. The area EFTF, it's energy which we are spent to overcome losses. GTTS, it's the additional work of expansion of more heated gas. And only one moment, what I want to say to you. I don't sure what it's really so, but in the textbooks deal with the turbomachinery, the authors says what the area CMND approximately equal to the area ETSTF. If these lines are parallel, I don't sure what it's true, but in reality, I think it's not far from the parallel direction. We could to say what these two trapezoids are equal. That's why we could to remove this one and add this one. So by other words, the ideal, the real work will be equal to this one. So of course we could do not extract this moment, and at this case, sorry, I need to change the color. So if we will directly read this equation, we need to add this one, and minus this. But if make the assumption what this area equal to this area, we could to change to the other area like this. So that's all about the energy transformation in the turbine stage. So we are discuss the energy transformation. That's why we could do speak about the efficiency, of course. Efficiency, it's the very typical definition for all area of the physics, and efficiency is the relationship between the useful work and supplying work, useful energy and supplying energy. And like useful work and what could be used like supplying work. We have a lot of type of efficiency, but in reality, in common in the thermodynamic process, we are use two type of efficiency: isentropic efficiency and polytropic efficiency. So what is the isentropic efficiency? We are divided all work which were spent to the compression. It's the work of ideal compression. We are divided it for all specific work which were spent in our process. And this type of efficiency are most useful in real practice. For example, at previous semester, you are study the engine cycle calculation. This the HEVA, this scheme. So, and inside this equation, you use efficiency for the compressor, efficiency of the turbine. Usually, it's mean isentropic efficiency. And of course, for example, in the design process of the turbomachinery, we are based to this way. We are trying to fix, to improve exact this way. But sometimes, especially in the thermodynamic calculations, could be used polytropic efficiency. It's taken account additional work of for compressing more heated gas, and this value more than isentropic efficiency. And as far as I understand, this efficiency are not depend from the sizes of blades, from the type of, not type, it depends from the type, from sizes, from conditions at first moment. And sometimes more useful to use this one. For example, as far as I know, the biggest value of polytropic efficiency which are reached in axial compressor approximately 0.90.5%. As far as I know, it's the biggest value which was reached ever. It was in engine year 3 from GE company. And now the high pressure, it's for high pressure compressor. And now this compressor used in the GE90 engine. It's the most powerful serial engine which I used at this moment. And the high pressure compressor of these engines are really example of the best compressors which are designed in the world till this moment. So, and the same approach for the turbine. The efficiency of the turbine is the relationship between the useful work and work of expansion process, and taking in account different energy of expansion process, you could to receive isentropic efficiency and polytropic efficiency. But of course, for us, for guys which deal with the turbomachinery, more useful is isentropic efficiency, because exactly this value are drawn right in the thermodynamic calculations, and of course, during calculation we are based to the data from thermodynamic calculation. So that's all about the thermodynamic process of the turbomachine. Very short topic deal with the equation of radial equilibrium. So, very typical approach for the turbomachinery to design stage what the particle contain in the layers. So I try to explain. You have the turbomachinery stage, turbomachinery blade row. It's not important, and you could split the main flow to the large number of layers. And it's a very good idea to realizing layering flow. What it mean? What? Sorry. Mean what if? Why? It's mean what it will be good idea. What if the particles come inside one layer, it doesn't need to change the layer, because if you change the layer to up or to down, it's mean what you need to spend additional energy, and of course it will be losses. So, how to realize layering flow? Let's imagine what we have random blade row, and we choose random particle, and we need to write the condition of layering flow. What it will be mean? It's mean what the particle doesn't change radial position. It's not move up, it's not move down. It means what the radial coordinate are constant. And if the particle doesn't move in radial direction, it means what all forces, the resulting of all forces which act along the radial x equal to 0. At this case, point will be at the same position if resulting force along the radius will be equal to 0. And that's why finally write the sum of the forces which act to the random particle along the x air. What kind of forces impact to this particle? It's pressure forces, like in one of previous equation which we discussed. It's the change of pressure along the radius multiplying to the area. Force which act to the blades, to the flow from the blades, that's one. And two types of centrifugal force. It looks a little bit strange, two types of centrifugal force, but in reality, the particle path line in the turbomachinery channel, it's the spiral line. The particle moves like this, using spiral. That's why it's have influence of centrifugal force with deal with the rotating around the axis of rotation. And the second, it's have influence of the centrifugal force which deal with the turning when it's moving forward. That's why we have two parts of centrifugal force. But I think it's not very important. If you want to study it, I write it in lectures, and I hope then you comes inside this site, canvas, I mean, you could to take the lectures text. So, it looks rather complex, but this equation are really used. For example, during CFD calculations, you could do in Fluent, if you work in Fluent, what you could to use radial equilibrium equation during calculation of the pressure at the outlet boundary condition. It's very useful for the turbomachinery calculating, but it's not a good idea to calculate the turbomachinery in Fluent. It's not very suitable for the turbomachinery. But if we will a little bit simplify this equation, we will write it for cylindrical flow without changing the radius. For the in the axial gap, it means we have no blades here, and it means we have no influence of the blades to the flow. And finally, this first equation of radial equilibrium could be simplified to this shape. And if we will look carefully to this equation, we could say what layering flow could be provided if we will organize radial pressure gradient in the channel. So, by other words, if we create increasing of the pressure along the radius, we could to realize layering flow. And as you remember from the Bernoulli equation, the pressure and velocity are changed to the opposite direction. If you increase in pressure, velocity are reducing. That's why the real distribution of the absolute velocity will be opposite to the distribution of the pressure. I don't sure what we will discuss about the radial condition, about the condition of the work of the turbomachinery stage in different radius, but it's have the great influence to the calculation of the parameters along the radius. So it's very short moment because I need to show to you this equation. I don't sure does we will discuss it in future lectures deal this course, but you could to find it in CFD calculation, for example, if you will provide it during your diploma work, for example. So that's all. So, and the last chapter, do you remember the velocity triangles? Why the velocity triangles are very important? Because it's contain a lot of information. They are set the shape of the blade, and looking forward, if you know velocity diagram, you could to calculate everything about your stage. That's why during design process of the turbomachinery, then you are complete your task. I'm going to start the design process of the turbomachinery, and you will see what if you know velocity triangle, you know everything about the working process. You could to calculate everything. That's why to know velocity diagram, and we will discuss how many parameters and which parameters we need to know to describe working process of the turbomachinery. Oh, sorry, velocity diagram and working process of the turbomachinery. So this is velocity diagram. At this case, more convenient to use the shape of velocity diagram, which typical for US turbomachinery school. So, how do you think? How many parameters we need to describe the shape of velocity diagram? Only suggestion. How do you think? In reality, it looks a lot of parameters. Yeah. And if we will say more complex, how many parameters you need to set to describe the working process of the turbomachinery stage? A lot of parameters, 100, and maybe I don't know. The position of the design process of the turbomachinery, designing velocity diagram, and during your future task, you will see what if you know velocity diagram, it's very easy to recalculate all parameters of the turbomachinery. So let's try to understand how many parameters we need to know. One second. Так, I lost. So if you look, stupid mistake. If you look carefully to the velocity diagram, it's a trapezoid. It's a trapezoid. That's why we need to find how many parameters and which parameters we need to set to describe the shape of the trapezoid. It's very simplified. So if you need to set the shape of trapezoid, you need to set height of the trapezoid. You need to set lower base, upper base, and position upper base relative lower base. And in reality, the position of these 2 points could be not the same. That's why it could be different heights for first point and the second point. So that's why we need, as far as I remember, 6 parameters. 6. Let's check. 1, 2, 3, 4. Something strange. Okay, we will try to find. And additional parameters which set the position of this base relative to this base, because it could be different. It's very interesting. In reality, it's very different, interesting. Okay, in any case, we could have independent parameters. If we divide all velocities to the circumferential velocity, to the value of lower base, we will receive dimensionless I remember the 6 parameters. So the U1 could be not equal to. That's why we need 6 parameters. So if we divide all parameters to U, the lower base will be always equal to the 1. Always. And it's very convenient because we are neglectate one variable parameters. We are reduce number of independent parameters. And let's look carefully to height of the triangle. We are receiving the height of dimensionless triangle equal to CA divided by U. Such parameters are called flow coefficient, because CA deal with the mass flow rate. That's why it's called flow coefficient. During your calculation, you will find what we have Smith charts which used flow coefficient to the it's how to say it's connect flow coefficient and load coefficient. We will discuss it right now. This the efficiency, and you will use it. So this is flow coefficient, and about the upper base. If you look here, it will be double VU equal to double CU. So in reality here, double VU divided by U. Why it doesn't work? It's really strange. It's decided to die. 1 second. Oh, 4 guys here, 3 guys here. So we need to reload the Так, сейчас, секундочку. So, and about the upper base, one second, in reality, it's the delta double VU divided by U. But if we will multiply all parts of this equation to circumferential velocity, we receive circumferential velocity at the second degree at the down part. But here, delta VU multiplying by U, what is it? This is Euler equation. And finally, this is a specific work of the stage. And that's why we receive a specific work divided by circumferential velocity at the second degree. These values are called load coefficient. So that's why what we are finally receive. If we take the assumption what the d1 equal to d2. It means diameter doesn't change, and it finally leads what circumferential velocity doesn't change. And if we will take assumption what C1A equal to C2A, it means what the height of these ears will be the same. That's why describing shape of dimensionless velocity diagram, to describing shape of this trapezoid, we need only three main parameters. Head coefficient, it's set the distance between the ears. Flow coefficient set the height of the triangle, and lower base equal to 1 always. Only one problem. We need to set the position of the upper base relative lower base. And we could use a lot of approaches. For example, you could choose one of the angles alpha 1, alpha 2, beta 2, beta 1. If you choose one value, you could find, you set the position and it solves the problem. But more physically correct to use other value. And you know it, we are discussing discuss it in previous lecture. If you remember, at last lecture, we received these two equations for the degree of reaction, for degree of reactivity. And if we look carefully to this equation, if we will set law and if we will set degree of reaction, we could extract C1U or C2U divided by U from this equation. And these values set the position of the upper base relative to the lower base. That's why more physically correct to use this degree of reaction, I mean like third value, because it's have physical mention. And it said, I refresh the information, what it said the relationship between the expansion work between the nozzle blade and rotor wheel, or compression work between the rotor wheel and guide wheel for the compressor. So, what it means? If you have constant middle diameter, if you have constant axial velocity, it's very typical for design process, you need only three parameters, three independent parameters to describe working process of the turbomachinery. So you choose three parameters and everything stage. At next chapter, I will show how to calculate it. It's really very simple. Of course, you could say, I know a lot of examples. I see the sketches, I see the real construction, this non-constant diameter, and maybe not all designers choose the constant axial velocity. No problem. You could set two additional parameters. One, set the relationship between the diameters. By other words, it set the shape of the flow path. The parameter number 4 set the shape of the flow path. And the last parameter set the value of meridional acceleration. So, that's why to describe working process of the turbomachinery, you need as minimum 3 parameters, as maximum 5 parameters. And you know everything about the turbomachinery stage. It's really so. And you will use it during calculation, but you will use only 3 parameters to simplify the calculation. Few moments deal with the dimensionless velocity diagram. So, how the changing of these 3 parameters influence to the shape of the velocity diagram? If you are increasing load coefficient, it means you are increasing distance between the ears. If you are reducing, the ears became closer. If you are increasing, it's move in the opposite direction. If you are increase flow coefficient, you are increase the height of the triangle. If you are reduce, you are make it more smaller. And then you are change degree of reaction, you are change the position upper base relative lower base. So it's mean like this. And the last idea here, it's the typical range of the parameters for the different type of the turbomachinery. You could to use, you could to not use. It's depends from you. So for us, it's most useful values for the axial turbines, for axial compressors. Where is it? This one. And typical velocity flow coefficient for this type of the turbomachinery. For axial turbine and axial compressor. But looking forward, how to say, about the Smith chart, few words. You will use it during calculation process, but let's this one. Not provided here. Sorry, I have no. Okay, I will find the next one. So, during calculation, you will use Smith charts. It looks like here. So here you at the as the lower x you have flow coefficient. Here you have head coefficient, and this line it's the line of the constant efficiency, and it's very clear to see at which position you need to set the point to receive high efficiency. And it really looks very simple. You are choose point here, and you are receive the best machine. But of course, in reality, you will have a lot of limitation, deal with the stresses at first case, deal with the some additional moment, because Smith chart are not taken in account of losses. And sometimes we need to set additional limitations, deal with the supersonic velocities, deal with the high flow turning angle, and a lot of other moments. So that's all about this chapter. In future, I want to prepare test, deal with it. So at this moment, I said send the invitation to you. Please try to come inside this site, and if you have problems, please write to me. I will write the letter about the velocity triangles task for your classmates, and soon I hope to start the test using this site, but it will be a test deal with the first chapter. And soon, then I will complete the translating the task for the next chapter. I will start the test deal with the next chapter. So the deadline for the triangles till this Sunday. That's all. So I think it's not we not need to start the next part because it's rather long discussion, and it's better to discuss without breaking. That's why we will At next lectures, we will discuss principle of operating of the compressor and the turbine, and of course, for all guys, it will be most important information from this course. And that's why I think it's will be explained without breaking, without stop. That's why that's all for today.